In this video, I will go over some helpful kinematics equations describing the relationship between displacement, velocity, and acceleration. In kinematics, for simplicity, we take the initial time to be 0. Del t is the same as t. And we can use either del t or just t in the equations. We use subscript 0 to describe the initial state, like this, and subscript f to describe the final state, like this. For simplicity, we can drop the subscript f and describe the final state with only the symbols like x for position, v for velocity. The other simplification we make at this stage is assuming that the acceleration is constant. When acceleration is constant, the average acceleration is the same as instantaneous acceleration. So when describing the acceleration, we only use the symbol a. In most cases, we can describe the motion accurately by assuming the acceleration is constant. If we have a motion where acceleration changes drastically, we can consider that motion in separate parts, each with its own constant acceleration. So for example, let's say we have a motion. Initially, we have 0 acceleration, and then the acceleration at this point changes to, let's say, 5. So we describe this motion in 2 separate stages, one with 0 acceleration and the other with acceleration equal to 5 meters per square seconds. From the equation, v, average v, equal to del x over del t, we can arrive at a new equation. First, we use the simplification explained earlier to arrive at v equal to del x over t, or x minus x0 over t. And then we solve for x. So then x would be vt plus x0. So this is our first equation. Also, when a is constant, the average velocity is the simple average of initial and final velocity, and it can be written like so. So average velocity would be v plus v0 divided by 2. Let's look at an example of how this new equation can be useful. Let's say we run from point A to point B with an average velocity of 6 meters per second in 100 seconds. If we assume initial position A to be 0, so x here is 0, what is the final position? What is the position at B? Let's use the equation we just obtained. X equal vt plus x0. V is 6. T is 100, x0 is 0. So this is 600 meters. We can do the same thing with equation A equal del v over del t. So this would be v minus v0 divided by t. And then we solve for v, and then we have at plus v0. Remember, that we are assuming that the acceleration is constant. Let's look at another example. We have a car with initial velocity 20 meters per second. This car accelerates at 2 meters per square seconds for 30 seconds. What is the final velocity? So let's use the most recent equation we obtained. V is AT plus V0. So V is 2 meters per square seconds times 30 seconds plus 20 meters per second. That would give us 80 meters per second. Now, let's obtain a new and very useful equation. We can use this equation when we have an object with constant acceleration and we want to find the final position. Let's start with our most recent equation. So V equal AT plus V0. Let's add V0 to either side of this equation and divide by 2. Now, we know that V plus V0 divided by 2 is average velocity. So let's substitute for that. We know that x is equal x0 plus vt. Let's substitute for v average velocity in this equation. Then we have x is equal x0 plus a2 at divided by 2 plus v0 times t. And that would be 1 over 2at squared plus v0t plus x0. So this is our new expression. The final position is half of a2 squared plus v0t plus x0. Let's see an example of where we can use this equation. We have a car that accelerates from rest. V0 is 0 at 10 meters per square seconds. So A is 10 meters per square seconds for 5 seconds. So T is 5 seconds. How far does this car travel in this time? So we need to use this equation that we just got. X is 1 over 2 times 10 times t, 5 to the power of 2, plus v0 is 0, so this would be 0, and x0, we assume it starts at the origin, so x0 is 0. So we have 5 times 5 to the power of 2, which is 125 meters. Another equation that is especially helpful when we don't have any information about time interval. We don't know. We don't know the time interval. In this case, we can use the following equation that can be obtained by solving the previous equation for the final velocity. Let's see. First, let's solve v equal v0 plus at for t. So t would be v minus v0 over a. Next, let's substitute t and average velocity. So t and average velocity, which is v plus v0 over 2. Let's substitute this into x equals x0 plus vt. So we're going to substitute this here and substitute this here. We're going to end up with x equals x0 plus v0 over 2 times t, which is v minus v0 divided by a. And when we solve for this, we're going to arrive at this equation. V to the power of 2 is equal to v0 to the power of 2 plus 2a x minus x0. As you can see, we don't need time to use this equation. Recall the last question where we found the final position of the accelerating car. Now let's find its final velocity without using the information about time. So in the last question, we had a car that accelerated from rest. So v0 was 0, a was 10 meters per square seconds, and this happened in 5 seconds, but we don't need time. And we found that the final position was 125 meters. We're going to use that here. Now I want to find the final velocity. So using this equation, v squared is equal to 0 plus 2 times 10 times final position minus initial position. And this will give me 2500. So v squared is 2500, which means v is 50 meters per second. Okay, I hope this video helped you understand different kinematic equations, how to obtain them, and their use in physics problems.